Well, good afternoon, everybody. Hello there, and welcome to the Academy's Morrison Planetarium, which, along with the Academy, of course, is located on the traditional unceded homeland of the Ramaytush Ohlone people, who are the original residents, the original natives of the San Francisco Peninsula. You're about to see our last planetarium show of the day, one of several that we offer through the day. And how many of you have seen our other presentations, either Expedition Reef or Dark Universe? A few. Okay, don't be embarrassed. It's okay. All right. This show is a bit different because it's entirely live. And what we're going to do is fly you through a 3D digital model of the entire universe, leaving Earth behind, flying through the solar system, flying out of our galaxy, and seeing where we are in the big picture of all the galaxies in the universe that we know of. And we're using a piece of software that is very accurate, and one that you can actually download for free and install on your computer at home. It's supported by NASA. And if you're interested in what you see on the dome overhead in the next half hour or so, come and see me up at the control booth. I'll tell you how you can get this software and where you can download it from. Now, what we're going to do is, again, fly through the universe out to the edge of the observable universe and back. We'll do it all by 5 o'clock because the museum closes then. But being a live flight, basically, the motion can be a little dynamic at times because of the immersive nature of a planetarium experience. The images go out to your peripheral vision. So sometimes the illusion of movement can be a little more effective for some people than others. If you find yourself feeling a little uncomfortable because of that, feeling any kind of motion sensitivity, just close your eyes for a minute or so and shut off that visual stimulus, and things should settle down. Those uncomfortable feelings should go away. As with all of our presentations, we do ask that during the show, you please refrain from eating, drinking, snacking, or any kind of photography or recording. This would also be a great time to silence your personal electronics and tuck away any light-emitting devices like cell phones, cameras, flashlights, etc. That light can be very distracting for the people sitting around you in the dark and can also interfere with the images that we project onto the dome overhead. So kindly keep that in mind. And at the end of the show, we ask everyone to please exit out through the doors at the top of either stairway. Either side works, and they all go the same way. And with that, we invite you now to settle back in your seats and make yourselves comfortable as we take off on our journey through outer space. And, one famous astronomer once said, outer space is not that far away. It's only about an hour's drive if cars could go straight up, which is true because the officially recognized boundary of outer space is 100 kilometers above the surface of the Earth. That's about 62 miles, or roughly the distance from San Francisco to Santa Rosa or San Jose. And so here we are, actually not 62 miles. We're 1 kilometer, a little less than that, above one place where people do leave our planet and go off into space. This is pad 39A at Cape Canaveral, which is where the space shuttle crews lift off from. And we're going to go about 100 times this altitude. We're at 1 kilometer right now. The official definition of outer space is of 100 kilometers. Why is it 100? Well, it was calculated back in the 50s that 100 kilometers is where the air is so thin that control surfaces like wings, rudders, flaps don't work. So you have to use rockets to maneuver. So up there at about 100 kilometers is where you can't use wings. They're not good for anything unless you come farther down into the atmosphere. But up at 100 kilometers, which is right here, this is the official boundary of outer space. So this is where you need to use rockets to maneuver around. And this is just touching the edge of outer space. The Earth's atmosphere expands and contracts because of the heat of the sun and other factors. And so it's not a hard, fast distance from the surface of the Earth. There's no sign up here that says outer space begins here. It's higher sometimes, lower sometimes. NASA, for some purposes, uses 50 miles rather than 62 miles. So a little bit less. There's a little bit of variation. But to be safe, let's go up to where the space station orbits, So about, let's see, about 4 times the official boundary of space. So up to 400 kilometers. That's roughly 250 miles. And right about here is where the space station orbits our planet. Up at this altitude, you can see a little bit more of the planet. You can see Florida right below us. And the space station is our current home away from home. It orbits the Earth about once every 90 minutes, traveling 17,000 miles per hour. Pretty quick. But that's the farthest that humans travel from Earth right now. In the next few years, humans hope to travel even farther away from Earth than that, as far away as we traveled back in the 1960s, between 1968 and 1972, when a few lucky astronauts were able to go all the way out to the moon. So let's travel farther out. We went from the altitude of the International Space Station, and we will go about 100 times that, or rather 1,000 times that distance. So let's see, we go from 250 miles above the Earth out to about 250,000 miles away from Earth, 250,000 miles. That's where the moon is, 250,000 miles away from Earth. And to find it, we're going to, let me turn on the moon's orbit so that we can figure out where we want to go. If I move things around too quickly, then that motion sensitivity that I talked about starts to kick in a little. So we can see the orbit of the moon around us, that arc up at the right-hand side, and the moon is actually right behind Earth, right there, at the end of the orbit, which we can see there. So I'm going to zero in on the moon. And let's take off. Let's go to the moon, traveling that 250,000 miles, 250,000 miles. It took the Apollo astronauts about 3 days to cross this distance. We can do it in just a few seconds. But there are some things that can go even faster than that. I'll talk about that in a second. So here's the moon, our nearest neighbor in outer space, 250,000 miles away. It's about 2,000 miles across. The moon is a big ball of rock, and you can see that it's very dry. It has no air, no atmosphere, no clouds, no water, although those dark patches used to be called sea. Well, they still are called seas, because people used to think that they were big bodies of water. So they were called seas and oceans, and some have really beautiful names like the Sea of Rains, the Sea of Tranquility, the Sea of Serenity, but they're not really seas of water. They're dry plains of dried lava. And you can see a lot of craters on the surface of the moon. This big one right here at the very center is called Copernicus. This crater is about 60 miles wide. So again, that's a useful distance for us to keep in mind, that the diameter of that crater is about the distance from San Francisco to San Jose, roughly. So that's a pretty big hole in the ground. And these craters were blasted out by the impacts of asteroids and other objects during the moon's history. But there are, again, plans to return to the moon in the coming years. India just landed a robotic spacecraft at the moon's south pole. Nobody's done that before. And they just did it roughly a week or so ago. Very, very interesting mission. And again, plans are for NASA to return astronauts to the moon. China has plans to go to the moon, so everybody wants to go to the moon. And we'll see how that goes. But let's travel even farther out than that. It took the Apollo astronauts, as I said, about 3 days to travel from the Earth to the moon. It took their radio signals only about 1.5 seconds, because those radio signals travel at the speed of light. And it takes light only 1.5 seconds to go from Earth to the moon. And as we travel farther and farther out into space, we will encounter distances that are so large that measuring them in miles, expressing these distances in miles, starts to get really nonsensical, because the numbers just get so big that it'd be like trying to measure the length of Golden Gate Park in millimeters. So we're going to use another measurement, a unit of length that astronomers use, called the light year. That's the distance that light travels in 1 year. And we can break that down even to smaller bits, like light months, light days, light seconds. For example, the moon is about 1.5 light seconds away. The sun, which you see appearing in the lower right there, is 93 million miles away, as we learn in school. So it takes light about 8.5 minutes to travel from the sun to Earth. And so we say the sun is 8 light minutes away. And if we travel farther out into space, we'll encounter even greater distances that are not just light minutes, but light hours, light years long. So as we back away from the center of our solar system and our location in it, you can see the sun at the very center with the inner planets, Mercury, Venus, Earth, and Mars. And after Mars, there's a gap which is filled with chunks of material called the asteroids. And there are several 100,000 named asteroids that astronomers have found in this area. But there are lots of other asteroids in different parts of the solar system too. A lot of them are just concentrated in this ring here. Beyond the asteroid belt is the realm of the giant planets. We start with giant Jupiter, and then comes Saturn, and then Uranus, and finally Neptune. And just beyond the orbit of Neptune, there's an area called the Kuiper belt. And the Kuiper belt is something like the asteroid belt, only it's a lot bigger. There's a lot more material here, and it's a lot messier. Here, there are objects that are largely comets with fairly short periods that return to the inner solar system within about 250 years or so. But there are other objects called dwarf planets, and there are a number of these objects out here, which some astronomers suggest could almost qualify as planets themselves, kind of like Pluto, which stopped being called a planet in 2006, but is now classified as a dwarf planet. But there are a bunch of these out here, and you can see some of the orbits are really wild. But this is all leftover material after the formation of the solar system 4.5 billion years ago. But we'll back away even farther than this, and I want to show you the farthest that any spacecraft has traveled from Earth. I showed you, how we went to the moon, how we sent people to the space station. Now, the farthest any spacecraft has gone from Earth is represented by these lines here. These are the paths of the spacecraft that are on their way out of our solar system. And we start with the Voyager, or rather the Pioneer 10 spacecraft, which is the one going off by itself in this direction. And all the others are going in the opposite direction. These include Pioneer 11 and Voyager 1, Voyager 2, and then New Horizons, which passed Pluto not too long ago. But these are the farthest that any physical representative of Earth has traveled from our planet. But there's something else that has gone even farther than that. As we travel farther out, we leave our solar system behind and enter the realm of the stars. We enter interstellar space, and as we travel between the stars, now we encounter distances that are so great that they are measured in light years. The nearest distance, the nearest star to Earth is one in the constellation Alpha Centaurus, the Centaur. It's the star Alpha Centauri, about 4.5 light years away, or about 25 trillion miles. 1 light year is 6 trillion miles. So a star that is 4.5 light years away is 25 trillion miles away. Its light takes 4.5 years to get to us here on Earth. And as we travel farther away, now we start to see other stars passing by as we travel through them. And at this particular distance, we can see the most distant evidence of humanity's presence in the universe, and that is represented by this sphere right here, this bubble of radio signals. For the past 90 years or so, humanity has been sending radio signals out into space, not all deliberately, some accidentally, some TV transmissions and radio transmissions that have leaked through the atmosphere, radio signals given off by the detonation of nuclear weapons, and in some cases, some intentional signals out to the stars. But this is as far as any radio signal has traveled, about 90 light years away from Earth. So if there are any civilizations on stars that are inside this radio sphere or radio bubble, they might have picked up our radio signals. Maybe it might be hearing old broadcasts. But if they're outside the radio sphere, they wouldn't know about us yet because our radio signals haven't gotten there. So that is as far as any human influence has traveled into the universe, 90 light years away from Earth. But the universe is a lot bigger than this. Let's travel even farther out. I'll leave the radio sphere on so that we can see where we are in the big picture of things. And as we do, we're going to travel far out, far enough away so that we can see our Milky Way galaxy. Now, up to about 100 years ago, astronomers thought there was only one galaxy in the entire universe. They thought that was it. But then Edwin Hubble showed that there are other galaxies far outside the Milky Way. And he also showed us that the universe is not only bigger than we thought, but it's getting even bigger still. The galaxies that we see in outer space are moving farther and farther away from each other. So that's just a mind-boggling thought. And that only happened about 100 years ago. We are located, there's our radio sphere at the very center. We are located nowhere near the center of the Milky Way. We're off to the side, about 2/3 of the way out from the center. And the Milky Way is a very thin disk of several hundred billion stars. It measures roughly 100,000 light years in diameter. So it would take the light of the stars at one edge, roughly 100,000 years, to get all the way across to the other edge. That's how big our one Milky Way galaxy is. But there are some other galaxies that are even bigger than this. And there are lots and lots and lots of other galaxies as well. The Milky Way belongs to a small cluster of several dozen galaxies called the Local Group. And this is a small cluster. There are other clusters that are even bigger that contain thousands of galaxies. And now that we've left the galaxy behind, every spot of light you see, all these colored dots, are not stars, but they're the locations of actual galaxies. And this is based on the actual data from surveys of the universe that have been made over the past several decades. And you can see how galaxies are clumped together into clusters, and some are off by themselves. But you get an interesting picture of the texture of the universe. If we back far away enough, you can see that there is almost a foamy or sudsy texture to the universe. There are filaments and tendrils of galaxies separated by large voids or empty spaces. There are big superclusters, clumps of lots and lots of clusters of galaxies. And the farther out we travel, the more amazing our map of the universe becomes. Again, this is our current map of the universe based on actual studies. And as we travel far out to get a really big idea of what the distribution of galaxies in the universe is, we see that the universe has an unusual shape, or rather our model of the universe has an unusual shape. Now, if we travel around, rotate to the right angle, it might look a little unusual because from as seen from along the plane of our galaxy, along from the right angle here, it looks like the universe has the shape of a giant butterfly or maybe a big bow tie. Is that empty space there between these two large fans going off to the left and right? Is that empty space really? Is it really empty space? Well, no, it's not. It's just areas in the universe that we haven't mapped very well yet because there's something blocking our view. And what's blocking our view is the dust and gas along the plane of the Milky Way. When we look along the plane of the Milky Way and look at that faint band of light crossing the sky, we're looking right along this band right here. And with all the dust and gas in the galaxy blocking our view, our model is not complete. So that's why it looks empty in this area. But we expect our technology and techniques to improve in the coming years so that we can see more uniformly in all directions, and our map will fill out a lot more nicely. But as we travel even farther out now, we encounter objects that are about 10 billion light years away from Earth. Some of the most distant objects that have been seen are what are called quasars, or quasi-stellar radio sources. Those are the orange dots you see at the ends, the big ends of those fans going off in opposite directions. Quasi-stellar radio sources are believed to be the cores of very, very young galaxies, newborn galaxies that are powered by supermassive black holes. And to be as bright as they are from the distance that we see them, they must be extremely energetic. And beyond that, the edge of the observable universe is represented by a faint radiation coming from all directions, filling the entire universe. This is something called the cosmic microwave background. It was predicted way back in 1948, discovered in the 1960s, and this is believed to be the first light that was able to travel from one place in the universe to the next. I mentioned earlier how Edwin Hubble discovered that the galaxies are spreading farther away from each other. Well, at some point, they must have started closer together, and astronomers did some calculations and figured that, well, at some point, the galaxies must have been squished together about 13.8 billion years ago. And that's when the universe was so hot, so dense, so compact that it was opaque. Light could not travel from one place to another. But then after the expansion began, a moment that some astronomers jokingly called the Big Bang, about 380,000 years after that, the universe began to become thinner and more transparent, more rarefied, and light was finally able to travel from one place to another. And this cosmic microwave background that we see surrounding everything, that is that first light. This is a very, very crude map of the temperature differences in the young universe, where the temperature differences are only several 10,000ths of a degree. But it's enough to show that this is when the matter of the universe began to differentiate, and this is how we got to the formation of stars and galaxies. So this is as far as we've been able to observe anything in the entire universe. And that being the case, the only place to go is back in where everything began, back in where we started from. And if it occurs to you that it looks like we've put ourselves at the very center of the universe, we're not. Our model surrounding us puts us at the very center because we're the ones who made the model. So it's based on our perception, the fact that we are looking out from where we are at everything surrounding us. If there were someone else in some other part of the universe, they would see the same thing. And their model of the universe would make it seem as if they're at the very center. But there are so many hundreds of billions of galaxies in the universe, according to these surveys and these maps that we have, and so many stars in each galaxy. And it makes you wonder, are there other planets like our own? Are there other solar systems like our own? And the answer to that is yes, there are. And as we move in closer and closer, we'll go to where we can see our radiosphere. That's our location in the Milky Way galaxy. And now I'll stop right here and show you a map, again, based on actual surveys of the extrasolar planets that have been discovered so far. These are the locations of stars that are known to be orbited by at least one planet. Each of these blue circles you see is a star that is a home to a planet or two or more. There's one system that's been found that has 8 planets in it. Are any of those planets like Earth itself? We really don't know. And it takes a lot. It kind of depends on what you mean by Earth-like. I mean, if it's a solid body, okay, that's kind of like Earth, but is it a world that can support life? That's a completely different question. And you need to fulfill a lot of different conditions for a planet to support life. It's got to be the right distance from its star. It's got to orbit the right kind of star that doesn't give off dangerous radiation. It can't be too close, can't be too far away. The planet itself has to contain the right types of minerals and compounds that can support life. And so there are lots and lots and lots of conditions that we need to fulfill in order to determine whether or not a planet can support life like our own world can. But so far, since about 1994, astronomers have discovered more than 5,000 other planets orbiting sun-like stars. Can you believe that? You know, if you ask a kid in school several years ago, how many planets are there? They would think of only one solar system, our own. And they would say, well, 8, maybe 9 planets. But nowadays, if you ask how many planets are there that we know about, there's a lot more than 5,000, including planets orbiting distant stars. So as we move back in toward the inner part of our own solar system, let me get rid of the extrasolar planet map. I'll also turn off the main belt of asteroids there. As we return to our own planet Earth, just think about what we've seen so far. We've been out to the edge of the observable universe and seen so many stars and galaxies and seen so many extrasolar planets. So far as we know, in all of our travels, we found only one, the one we came from, that has the conditions that can support life. So as we traveled farther out to the edge of the universe and back, we find that there is literally no place like home. And so with that, welcome back home to planet Earth, and we hope you've enjoyed this tour of the universe. Thank you very much.